Okay, so here we are back at parametric equations of lines. Remember that our goal is to get to the Spring 2017 Stanford Convolutional Neural Networks for Visual Recognition course as soon as possible. Here you can see, by the way, where we're trying to head towards. This is an example of a convolutional neural network or a deep learning algorithm, which takes an image here and tries to classify it. So here it says this is a truck, most likely a truck. It says this is most likely a truck. It says this is most likely a deer, and so on. So this is an example of deep learning, and we're heading towards this, but we have to cover the groundwork first. So let's get into this. Parametric equations of lines. So let's see an example first. Let's look at this one here, example 2. So hopefully you're familiar somewhat with the cosine function and the sine function. And you know that when you put in values into the cosine, between 0 and 2 pi, or if you like, between 0 and 360 degrees. Remember, 2 pi is the same thing as 360 degrees. So when you do that, basically you're taking the cosine of various angles between 0 and 360 degrees, or between 0 and 2 pi. Same thing. Means the same thing. Then you're going to get an output from this here between -1 and 1. For example, the cosine of 0 degrees is 1. That's basically the x-axis. So it's 1. Whereas when you go to 90 degrees, or pi over 2, the cosine is 0. So you're going from 1 to 0, then you're going to go to -1, and so on. So anyway, so as you let t take on different values, both x and y will assume values. So when x and y assume values, it means you're getting different points in the plane. And it turns out that if you use these two equations to generate your x and your y, you will trace out, the points will trace out a circle. Okay, and we could show that. In fact, I think they show that here. In this case, it's a circle of radius 2. Anyway, this is an example of what we mean by parametric equations for a curve. Means that both x and y depend on some variable t, and as t changes, both x and y change, and you get some curve, in this case in R2 in the plane. And this is a general situation where x and y are functions of t. So going back to this, it says in R2 we know that equations like this is a line. This is also a line. These describe straight lines. These are not parametric equations, though. Consequently, one might expect that the same sort of equation to define a line in R3 as well. Consideration of a simple example should convince you that a single such linear equation describes a plane, not a line. A pair of equations in x, y, and z is required to define a line. So if you have a single equation in R3, that means in x, y, and z, for example, it won't define a line, it will define a plane. It's just like this defines a plane. Okay. It says we postpone the discussion of derivation of equations of planes till section 5. Okay, so here they tell us what they mean by parametric equations. So x and y are defined in terms of a third variable, which they're calling t. And this is an example. Okay, we don't need to deal with that. And here, x, y, and z are defined in terms of t, and that will give you some kind of curve in R3. So, for example, So down here, later, they're going to show that these equations here are going to give us the are the parametric equations for a line through this point and parallel to this vector. So what does that mean? So if we go back to a picture like this one, so when we're talking about a line here, we can identify that line by giving a point that it goes through and also saying that it's parallel to some vector A. So if I tell you that the line is parallel to this, and I also tell you a point that goes through that line, then you know which line I'm talking about. There are not two lines that can do that. So in order to identify a line, you could just give a point on the line, one point, and say the line also has to be parallel to some given vector. Okay, they say the advantages of using parametric equations are twofold. They offer a uniform way of describing curves in any number of dimensions. How would you define parametric equations for a curve in R4, in R128? Well, it's kind of clear. You'd go, instead of just these three, you'd have 4 or 128 variables here. Second, they allow you to get a dynamic sense of a curve. So that just means that, like when we use the one before, this one, as t starts at 0, we start here, and as t increases, we actually go along this path. So we kind of have a path or a direction for the circle. Normally if you just see a circle, you don't think, well, you have to start here and go in this direction. But if you use this to define it, as t increases, you do move in this direction. So it allows you to kind of give a direction to the path as well. So she says you get a dynamic sense of the curve if you consider the parameter variable t to represent time and imagine that the particle is traveling along the curve, or that a particle is traveling along the curve with time according to the given. So that's what we just said. You can represent this geometrically by assigning a direction to the curve. So we could say there's a direction moving around. Okay. Okay, so next we're going to talk about what we just did here. They're going to say, how can we provide equations for lines? For example, in R2 or in R3, you can see that a line is uniquely determined if you give two pieces of geometric information, like we said. If you know that there's a point, and you know that it's parallel to A, that's uniquely determines just one line, right? So a vector whose direction is parallel to that of the line, and any particular point lying on the line. In figure 1.23 here, or I'm sorry, 1.23 or 1.24. Sorry, in 1.23 we see that. In 1.24 we seek the vector r, which goes from O to P, here, O to P, between the origin and an arbitrary point P on the line L. So here we're trying to find the vector r. Okay. OP, this OP, is the vector sum of this plus this, right? If you take this plus that, you get this. Any vector parallel to A, here's A, must be a scalar multiple of A. Letting this scalar be the parameter variable t, we have r, this, equals OP, that's OP, equals OP0 plus TA. So there's some t that we can fill in here, that when we take this vector plus t times a will give us this. So we can write that r equals this, and we have established the following proposition. Oops. This proposition here, which basically says that this defines a line. The vector parametric equation, so it's a vector equation, because it has r and a, and it's a parametric equation because it has a t. So the vector parametric equation for the line through the point, through this point, which is here, P0, whose position vector is this, OP0, and, which is equal to B. So we just define OP0, call it B, And parallel to A is written like this. So instead of OP0, we'll write B. So we have R of T, because R depends on T. So R of T equals B, that we call this B, plus TA. So this is the vector parametric equation. So it's a vector parametric equation of the line through the point P, through this point P0, which we also call B, and whose position vector, and is parallel to A. So here. All right, so that defines the line, A line. If we expand that equation, we can write B as B1I plus B2J plus B3K. So B we can write like this. B is equal to some combination of I, J, and K, which is all they did here. And A is also equal to some combination of I, J, and K, so they're just going to put this here. They're just going to write that out here. So we get R equals this, some combination, and another combination. So we just have that. And then we can collect the things that multiply the I, which is B1 and TA1. So we get A1T plus B1I, and then collect the things that multiply J, and collect the things that multiply K. We get this. And now R, don't forget R. R was where? Here was R. So this is OP. Do we have an expression for OP yet? Not yet, but we'll just say that this is some, this is obviously some combination of I, J, and K as well. So we're going to call it, some combination of I, J, and K. We're going to call it X times I, and so we're just going to use these. So before we used like B1, B2, B2. Here we don't use subscripts because we're thinking of these as changeable or variables, whereas these we think of as fixed. So in other words, going back to this picture, this is, the point is fixed, but we're going to let this point P move along here depending on what T is. So that's why we use, instead of fixed like this, we use unfixed here. So anyway, we can write out something for this, like this. So then we have an equation with I, J, and K on this side, and also an equation with, we have an equation with I, J, and K on this side, and I, J, and K on this side, so we can equate the parts that multiply the i's. So that's what they do here. So X on the left side multiplies the I, and on the right side we have this multiplies the I, so they must be equal. So we get this, this, and this. And that is our parametric equations for the line that we've indicated before in the previous picture. Now they say that you can do this in Rn just as easily, and you'll get something very similar to this, but you'll get n equations. So let's try this. So to find the parametric equations of the line through a point, so we give them this point, and parallel to a vector, so we're given this vector. So what do we have to do? We have A is our what? A is the vector, right? Wasn't that the vector that we wanted to be parallel to? Yeah, A is the vector. So that's TA there. So A is the vector that we want it to be parallel to, and the point B, or the vector B, is over here. This is B, so P0. So the point, in other words, it's the point that we're given. We're given the point here. So the corresponding if we write it as a vector, it looks like instead of 1 comma negative 2 comma 3, it's 1 times j, negative 2 times, 1 times I, negative 2 times j, and 3 times k. So we get this. Same thing as the point. Then we put that all into here like we did there. We have, basically then we get a1 and b1. So what's our a1 is pi, and our b1 is 1, and our a2 is negative 3, and our b2 is negative 2. So we just fill these in, and we get hopefully this. So pi and 1 and blah blah blah. So we get this. So now we have the parametric equations. So find the parametric equations of the line through this point and parallel to this vector, and we have them here. So what we mean now is if we put in different values of t, we're always going to be on that line, on this line that we mentioned up here. And actually there's also kind of a direction to this line, as we said earlier. As t increases, we'll be moving in a particular direction along the line. But anyway, that's maybe not so important, but what is important is that we generate a line in R3, this was all done in R3, with these parametric equations. Okay, I will let you read through this example, but here, if we're given, so in the last example we were given a point and a vector, and we found the parametric equations, but we could also be given 2 points, and hopefully we can still find the parametric equation. We might have to do a little bit more work, because what we might do is take the 2 points and get a vector, and then do the same thing that we did in the last problem. But anyway, I'll let you read through this one and get either this, or I guess this can be simplified, or I'm not sure, but anyway, it looks like there's 2 different forms. Obviously, here, actually, I'm not sure why are we getting 2 different sets, but I'm not going to worry about it. If you want to think about it, you can. I want to keep moving. So just exactly like the last example, if we're given 2 points, get the parametric equations, and I go through the same thing we just did, and you get this. Okay, so here they emphasize that point, that is that you're not stuck with just one set of parametric equations. They are not unique. The equations are not unique. Example 4 brings up an important point, namely that the parametric equations for a line, or more generally any curve, are never unique. In fact, the 2 sets of equations calculated in example 4 are by no means the only ones. We could have taken a equal to, I guess we could have gotten a different a, or anyway, they're not unique. However, they say if parametric equations are not determined uniquely, then how can you check your work? In general, it's not so easy to do, but in the case of lines, there are 2 approaches to take. One is to produce 2 points that lie on the line specified by the first set of parametric equations, and see that these points lie on the line given by the second set. So then you would know that the first set is equivalent to the second set. The other approach is to use the parametric equations to find what is called the symmetric form of a line in R3. From equations 2, assuming that AI is non-zero, whereas equation 2 here. So if A is, basically we want to solve for t here, solve for t here, solve for t here. So in order to do that, we're going to have to divide by A1, we're going to have to divide by A2, we're going to have to divide by A3. So we want to assume that we can do that. That is, we want to assume that they are not 0, so that's what they say. So the other approach here, from equations 2, assuming that each AI is non-zero, one can eliminate the parameter variable t in each equation to obtain this. In other words, you can write t equals that, t equals that, t equals that, And then since these are all equal to t, you can equate these, and you get this. That's called the symmetric form of the line. And in example 4, the two sets of parametric equations give rise to corresponding symmetric forms, this one and this one. It's not difficult to see that adding 1 to each side of the second one yields the first one. In general, symmetric forms for lines can differ only by a constant term or constant scalar multiples or both. So then you have something more or less unique for the, so the symmetric form is more or less unique, not exactly unique because you can add, they can differ by constant or differ by a multiple, but except for that they're unique, or to that degree they're unique. Then she says the symmetric form is really a set of two simultaneous equations in R3. So that we have this equals that, that's one equation, and this equals that, that's a second equation. So this equals that, and this equals that. This illustrates that we require two scalar equations, so these are not vector equations, two scalar equations in x, y, and z to describe a line in R3, although a single vector parametric equation, we saw that before, a vector parametric equation was equation 1. This is a vector parametric equation. We only need one of those to describe the line. But if we're going to have scalars, not vectors, we're going to need two. Although a single vector equation, but we need two scalar equations to get a line in R3. Okay, so one thing we might want to do is find the intersection of a line and a plane. So you can have a line and you can have a plane, and you might wonder where they intersect, if they intersect. Another thing you might want to do is if you have two lines, wonder where they intersect. So let's tackle both of these problems using parametric equations. So of course we know how to do that, for example, we certainly know how to do this one in R2, find the intersection of two lines, but first of all we're talking about in R3, and second of all we want to do it with parametric equations. So let's see, example 5, we find where the line with parametric equations, so this is a line, parametric equations for a line. I guess we can go back and check the form to make sure that it really looks like a line, but and we want to see where that intersects this plane. This is a plane. So we want to find the point of intersection. So what they do is they say to locate the point of intersection, we want to find the value of the parameter t that gives a point on the line that also lies in the plane. So we have the plane here, this is the equation for the plane. So what we're going to do is we're going to take for x, we're going to replace x by this, and we're going to replace y by this, and z by this in here. So we're no longer going to have an equation in x, y, and z. We're going to have an equation in t, which we can solve for t. So solving that for t, we get t equals -2. Setting t equals to -2 into here gives us an x, y, and a z. Gives us 3, 0, 1, which indeed lies in the plane as well. So you can check that, well, we can see that when t equals -2, that we get this. So that means that this is on the line. And we can also check to see that it's also in the plane. See that it satisfies that equation. Okay, let's do just one more. We determine whether and where the two lines intersect. So this is a line, parametric equations for a line. This is another one. Maybe they intersect. If so, where? So the lines will intersect provided that there is a specific value for the parameter, specific value t1 for the parameter of the first line, and a value of t2 for the parameter of the second line that generate the same point. Now, these t1 and t2 don't have to be anything like the same. We just want to, there should be, if we we want to find a t1 here and a t2 here, that will give us the same x, y, and z. Then, of course, these two lines intersect. But it doesn't mean that t1 and t2 have to be the same. In fact, they won't be the same, generally speaking. But there should be a t1 and a t2 that give us the same x value. So that means that t1 plus 1 should equal 3t1 minus 3. That is this. And then you can do the same thing here and get this and this. So now we have, what, 3 equations with 2 variables, t1 and t2. Now, there may not be a solution to this. You probably know that. But there might be a solution to this, and if there is, then there will be an intersection between these two lines. And the next thing they do is they focus on these two, and those two give us this. Somehow I didn't check it, which somehow implies this. So t1 has to be equal to -1. Using t1 equals -1 in the second equation, we find that t2 equals 1. Okay, now we have to check. Note that the values t1 and t2 also satisfy the first equation of 9. Therefore, we have solved the system. In other words, we found t1 and t2 that satisfy this, this, and this. So there is such a pair, t1 and t2. So we do have an intersection, and we can figure out what that intersection is by, for example, putting in t1 here, and t1 here, and we'll get some x, y, z. We should get the same thing if we put in t2, t2 here. We should get the same x, y, and z. So I guess they do that, and they find that they intersect there. Okay, that's the end of this. We will next come to parametric equations in general, and we'll do that in the next video.